Hi there, Mr. Sutton here, bringing you the AB Calculus 511 Extra Practice number 4 solutions on FTC integral evaluation with non-polynomials. For this problem, we're told that f is not differentiable at 5. We want to know which statement must be true based off of this. So this is one of those, just go through and eliminate what you can. So for the first choice here, f is not continuous at 5. Well, there are different ways to be not differentiable. Certainly not being continuous is one of them. But there are non-differentiable spots that are continuous. For example, we could have a cusp at x equals 5. So this is not necessarily a true statement because we could have a continuous non-differentiable spot. Next choice, limit does not exist at x equals 5. Well, if the function is continuous, which we discussed that it could be in choice A, then the limit is going to exist. So this one, if you're not allowed to use the whole not continuous argument, this argument is also dead in the water. Okay, this next one now, this is basically the Leibniz form. This is saying that f prime of 5 does not exist. If a function is not differentiable, then you can't take the derivative at that spot. So this is a true statement. So probably going to be the answer, but let's look at choice D. This is saying the integral from 0 to 5 does not exist. Well, if you are continuous on 0 to 5, then you're guaranteed to be able to find the area under the curve. So this is definitely going to exist if our function is continuous, which it could be. So we can't choose this one either, and it's just choice C that's necessarily true. For this problem, we're given dy over dt right here. It's this e function. And we want to know by how much y changes as t changes from 1 to 6. So if we have a rate of change, to figure out the change in the original quantity, we just have to take the integral of that rate of change over whatever interval this thing is changing on. So really, we just need to take the integral from 1 to 6 of dy over dt. And let me go ahead and do that on the calculator now. So here I am in my calculator. I went to my y equals and entered the function that they just gave me for dy over dt in my y1. Now I'm just going to take the integral of that from 1 to 6. So let me quit out of there. Let me just do math 9 for integral. And again, we're going from 1 to 6. And let me just do alpha trace to pull up my y1 that I just stored that function in. Put a little x here for dx, press enter. And it comes out to about 22.583. So that's all we had to do on that one, choice D. For this problem, we're given this piecewise function f, and we want to know the value of the integral from 0 to 7 of f of x dx. All right, so this is a little bit tricky because we're being asked to find the area under a curve that has different rules at different times. Now, the tricky part about this, there's a few tricky parts. One of them is that we have potentially some discontinuities in here. But since these are going to be jump discontinuities, since there's nothing in here that's going to give us an asymptote, we can still find areas even if we're jumping from one spot to the next. So what we're going to do is we're going to split up this integral using these different rules. So I need the integral, for example, from 0 to 3 of negative 1 dx plus the integral from 3 to 5 of 1 dx plus the integral from 5 to 7 of 3 dx. So I'm just giving them each their own little domain here. So each of these is actually just going to be a rectangle if you're just taking the integral, finding the area under a constant, and the base of the rectangle is just going to be the interval length. The height of the rectangle is just going to be this number in the integrand. So for this first one, we essentially have a rectangle where we're doing a base of 3 times a height of, well, negative 1. It's negative value. It's under the x-axis. This next one, we've got a base of 2 times a height of 1. And this one, we have a base of 2 times a height of 3. So adding these all together, we have negative 3 plus 2, which is negative 1, plus 6, which comes out to a grand total of 5. So that's going to be choice A. On this problem, f is a differentiable function such that f of 1 is 2 and f prime equals this crazy expression. Based off this, we want the value of f of 4. So we're going to basically use the fundamental theorem to evaluate this thing. I have a starting value for f, and if I use an integral, I can figure out the total amount of change in f between x equals 1 and x equals 4. So I can say f of 4 equals my starting value of 2 plus, now to get the total change from x equals 1 to 4, I just have to add the integral of the rate of change of f, the integral of f prime from 1 to 4. And let me just plug this in the calculator now to see what that comes out to. To make my life a little bit easier, I've entered this f prime as my y1 in the calculator. And now let me quit out of there, and I'll do 2 plus math 9. So where we go, there we are, math 9. Integral from, we need 1 to 4. And we're going to do alpha trace y1, because that's where I stored f prime. And then a dx, and that's all I have to enter. Just press enter now. Comes out to 10.790 if we take it to 3 decimals. So that's going to be choice C. For this problem, f is a function whose first derivative is given by f prime equals sine of x cubed on the interval from 0 to 2. We want to know at what value of x f attains its maximum value on the closed interval from 0 to 2. So if we're talking about maximum values on closed intervals, generally that involves the candidates test, but that's a little bit tricky here because if you're going to do the candidates test, it helps if you can actually figure out what f of some different things is going to be. But we don't know a whole lot about the f function. All we have is f prime. We don't even have an initial value of f. So this is going to be tricky indeed. But just to see what's happening here, I'm going to graph f prime on my grapher and at least see how many critical values we're dealing with. So here I am in my y equals. I've entered the f prime function as y1. Let me just graph this out on the interval from 0 to 2. So let me pull up window, and I've got my x min is 0, x max is 2. Let me do zoom fit and see what we're dealing with here. So here's the f prime function, and it looks like we've got 1, 2 critical values. Now the important piece here, if you're looking for a max, you're only looking for local maxes in terms of these critical values. And we can see that f prime is changing positive to negative, which is how you find a local max, at just this one spot right here. Let me do second trace and zeros to see exactly what that x value is. So let me see, click ones to the left, ones to the right, one more for good measure, and that's about 1.465. So there's my graph, and I'm going to actually store that as a value on my calculator. I feel like I'm going to have to enter it at some point. So let me actually go back here, and let me quit out of this. Let me go to store, and that's going to store the answer I just got as, we'll do alpha A. There we go. So now I've got it stored away. All right, so this is getting trickier and trickier. We've got a local max here, which is great. Unfortunately, because we have more than one critical value, it's kind of tough to say that this local max is also the absolute max. We still have to use something kind of like the candidates test here. But again, the candidates test is very tricky if you can't get exact values of the different inputs. But if we were to use the candidates test, what would we have to do? Well, we would certainly have to test out the critical value in the original function to see what it gives us. We'd also have to test out the two endpoints, 0 and positive 2. So we are actually going to use the candidates test, but we're going to modify it a little bit. I don't know what the starting value is. I don't know what f of 0 is. That is a complete mystery to me. But I can at least talk about how much the f function is changing as we travel from 0 to 2. So although I don't know what f of 0 is, let me at least consider f of a. F of a, that's my local max here. That's going to be whatever f of 0 is, plus the integral from 0 to a of f prime. Now again, I don't know what f of 0 is, but I can calculate the value of this integral, so I can at least see how much I'm gaining or losing to whatever the value f of 0 is. And that will allow me to compare this f of a value to this f of 0 value, depending on whether we're gaining or losing something with this integral. So let me go back to my calculator now. And on my calculator, I'm just going to plug in this integral. So I'm going to do, let's see here, math 9, integral from 0 to alpha a, and then we're going to do alpha trace y1 to get my f prime in there, and dx, and that comes out to about 0.591. So this whole thing then I could write as f of 0 plus 0.591. Now, without knowing what f of 0 is, we can at least say that f of a is bigger than f of 0. And that makes sense, because if your f prime is positive, which we can see on the graph here, f has been doing nothing but increasing between 0 and point A here. The question, though, is this the highest we can get? Because although this is higher than we started, we also have this other endpoint to consider. And yes, we are decreasing for the original function because f prime is negative for a while, but then f prime becomes positive again. So we have to at least consider this other endpoint. So to consider it, to talk about f of 2, I'm just going to represent that as f of 0 plus the integral from 0 to 2 of f prime dx. And let me see what this 0 to 2 integral looks like on the calculator. So here I am on the calculator again. To save a little bit of time, I'm going to yank my input from before, and instead of going from 0 to a, I'm going to go from 0 to 2. And this comes out to 0.452. So this is f of 0 plus 0.452. So just ranking these in order from least to greatest, f of 0 is definitely the smallest one. F of 2 is the next biggest. You're adding 0.452. But even f of 2 is less than f of a, which was f of 0 plus 0.591. Because of this, we can conclude, without knowing what the max actually is, we can conclude that the max at least occurs at this x equals a, or that was 1.465. So that's going to be answer choice C. For this calculator-based problem, we're given the first derivative of g prime is this function right here. And if g of 2 equals negative 7, we want to know the value of g of 5. Well, g of 5 is just going to be this g of 2 value, negative 7, plus the total change in the function between x equals 2 and 5. To get that total change, we're just going to add the integral of the rate of change, integral of g prime of x dx, from 2 to 5. And I'm going to do all of this on the calculator now. To start this process and make my life a little bit easier, I'm going to put g prime in as y1 on the calculator. And then quitting out of there, I'm going to do negative 7 plus math 9. So that gives me the integral from, we said, 2 to 5 of, let me do alpha trace y1 to get my g prime in there, and a dx. Press enter. Comes out to about 13.899, which is one of the answer choices, choice C. For this problem, we're given this piecewise function for f, and we want the integral from 0 to 8 of f of x dx. Now, of course, this interval is going to span multiple rules here, not just one rule, so we're actually going to have to use all of these. Now, because this is a piecewise function, we do run the risk there are some discontinuities, but that's actually not going to stop us from finding the area, because a jump discontinuity, you can still work around that when you're calculating area under curves. There's no infinite discontinuities, no asymptotes on here, so we don't have to worry about discontinuities. What we do need to do, however, is split up this integral. So I'm going to have the integral from 0 to 2 of 2 dx. That's my first rule there. To that, I'm going to add the integral from 2 to 3 of 3 dx. And finally, I'm adding the integral from 3 to 8 of negative 1 dx. Now, the nice thing about all these is that these are all just going to be basically rectangle areas. These are all horizontal lines that you're graphing. So the area under them is just a rectangle with a base equal to the interval length and a height equal to, well, whatever the constant is. So for example, this first one, this is just a rectangle with a base of 2, because 0 to 2 is a distance of 2, and a height of 2. So we can say 2 times 2 for that. For this next one, we have a base of 1 times a height of 3. And finally, this is going to be a base of 5 times a height of negative 1. Just adding all that up, we've got 4 plus 3, which is 7, minus 5, which is 2. Choice A. On this problem, we have a differentiable function f such that f of 1 is pi over 2 and f prime equals this craziness. We want the value of f of 3. So f of 3 is going to equal this value at 1, namely pi over 2, plus the total change in the function between x equals 1 and 3. To get that total change, we're just going to add the integral from 1 to 3 of f prime, the rate of change. And let's just do that on the calculator now, because we can. To do this cleanly, I've entered my f prime here, 3 arctan of that quadratic, inside my calculator in my y1. And then let me just quit out of there, and let me do pi over 2. So fancy fraction mode, we've got a pi over 2. Plus, let me do now math 9 to get my integral from 1 to 3 of alpha trace y1 dx, enter, and that's going to come out to about 2.899 if I round it off, which is going to give me choice C. For this free response problem, we're given the f function, which is defined from -5 to 5. They're telling us f of 1 is 3, and they gave us the graph of f prime up here, which they said has 2 semicircles and a couple line segments. Our first task is to find all the values where f has a relative max, with justification. So if I want to know where f has a relative max, I need to know where f prime is changing from positive to negative. So looking at my graph up here, I see that f prime changes positive to negative at x equals -3 right there, and also if we keep going at x equals 4. So therefore, f has relative maxima at x equals -3 and 4. On this part of the problem, they want all values of x at which the graph of f has a point of inflection, with justification. So f is going to have a point of inflection. There's 2 ways to tell this: if f double prime changes sign, or if f prime changes direction, or I should say reverses direction, if f prime goes from increasing to decreasing or decreasing to increasing. So looking at my graph of f prime, I see that f prime changes inc to dec or dec to inc at the following places. We have a horizontal tangent here at -4, so there's one spot. Also, we have a direction reversal down here at -1. We went from decreasing to increasing. And finally, up here at this corner, we went from increasing back to decreasing, so at x equals 2. Since f prime reverses direction at all these values, it follows that f has points of inflection at these 3x values. For this problem part, we want to find all intervals where f is concave up and also has a positive slope. So in order to figure this out, again, just using f prime, because that's what they gave us all this information about with this graph, we want to find the places where f prime is positive, because we want a positive slope, so f prime has to be greater than 0. We also want to know where f prime is increasing, because that would give us concave up for f. So we're looking for f prime positive and increasing. So that's going to happen on a few intervals. We've got this interval right here from -5 to 4, where we are both positive and increasing. And as we keep going, now we're decreasing, now we're negative, 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 increasing and positive again between 1 and 2. And then we're decreasing for the rest of this and or negative, so not really what we want. But we at least have these 2 intervals here. Since f prime meets these properties on these 2 intervals, that means that f is going to be concave up and have a positive slope on those intervals. So there we have it. For this last part of the problem, they want the absolute minimum value of f of x over this interval. So we're going to start by getting critical values, and we'll test those along with the 2 endpoints, -5 and 5, using our candidates test. So in terms of critical values, we're looking for places initially where f prime equals 0. But if you look at it, there's a lot of places where that happens. At least between the endpoints, we have 1, 2, 3 critical values. So we don't want to have to test all 3 of those. The way I'm going to get out of this is I'm going to say f prime changes from negative to positive, which is going to give us a relative min, only at x equals +1. So because I've specified this already, I'm basically saying, hey, I'm only going to test out relative mins because nothing else is worthy of consideration for being an absolute min other than possibly the endpoints. So I'm going to test out x equals 1 along with -5 and +5. Let's do x equals 1 first, f of 1. The reason I'm doing that first, it's the easiest one. They told us f of 1 equals 3. So we get that one pretty much for free. So now 3 is the number to beat. And remember, we're looking for absolute mins. We're looking for something lower than 3. Let's check out f of -5 next. That's going to be this value of 3, namely f of 1, plus the integral from 1 to -5. So to do that, I need some areas here. So I've got 3, just like I had before, and I've also got this area of the semicircle over here between -5 and 1. But since we're going backwards from 1 to -5, because our higher number is the lower limit of integration here, that means I'm actually going to be subtracting all these areas here. So this would have initially been a positive area, but now it's going to be negative. I'm going to have minus 1/2, because it's a semicircle, 1/2 pi times 1 squared. And then we have this semicircle below the x-axis. Now normally this would have been negative area, but again we're subtracting because we're going backwards. So this negative becomes a positive area plus 1/2 pi times 2 squared. So we've got basically half a pi plus, let's see, 4 over 2 is 2 pi's. So minus 1/2 plus 2, that's going to be 3/2 pi, 3 pi over 2. And we're adding that to 3 here. So this number, I mean, you might not know what this comes out to exactly, but this is this other number plus a positive. So we know that 3 plus 3 pi over 2 is going to be greater than 3. So this number we just got cannot be the absolute min. So far it looks like 3 is still in the running, but we have one more candidate to consider, f of 5. That's going to be f of 1, which again was 3, plus the integral from 1 to 5 of f prime of x dx. And what is that integral? Well, we have two triangles here. Now we're going from left to right, so positive area is going to stay positive, and the negative area under the x-axis is still going to be negative. So we have this first triangle. This is going to be 1/2 times a base of 3 times a height of 2. And let's see here. We've got this other triangle. Now we're subtracting 1/2 times a base of 1 times a height of 1. So we've got 3 plus, let's see, 1/2 and 2 cancel, so just really 3 plus 3, which is 6, minus 1/2. That's 12 halves minus 1/2, or 11 halves. So this is a number that's bigger than 3. 3 would have been 6 over 2. So out of all these numbers, that means that our absolute min is going to have to be at 3.